Hello and welcome to a new lecture of classical motion of a single particle. In this lecture, we will try to extend our previous discussion on fixed points and phase space trajectories in the neighborhood of those fixed points. So, before starting the main content of this lecture, what I would like to do as usual to recapitulate a little bit what we have discussed on this topic of fixed point and the phase space trajectories. So, if you remember, I said that in the realm of classical mechanics, actually you have this type of equations of evolution or you have the equations of dynamics. Okay. This is a two dimensional phase space which basically gives you the motion in one dimension real space, okay, and of course for every real space dimension you will have one corresponding velocity. Okay. So, that is why whenever it is concerning 1D motion in classical mechanics, it is actually the motion or evolution of the system in 2D phase space, okay, which we sometimes also call as a 2D flow. So, for classical mechanics, the first equation is trivial because that is the ddt of the first phase space coordinate x is exactly equal to the second phase space coordinate itself, which is v. Now, the ddt of the second phase space coordinate v is equal to some f which can be a function of both x and v. Now, we took an example where actually one of the very familiar cases that you have this f to be just a function of the space coordinate only and not the v. Okay. So, we simply say that we are now talking in terms of our usual knowledge of classical mechanics, that a particle is moving under a potential u, okay, which is given by this minus x square by 2 plus x to the 4 by 4. Okay. And then just by using the concept of potential, you can derive the gradient of that potential to be the force on the particle, which is minus du dx, and that will be given by x minus x cube. Okay. Then we were trying to find the fixed points for this system, and according to the definition of fixed point, if you remember, we said that a fixed point is a point where both these velocities x dot and v dot, that means ddt of the first phase space coordinate and ddt of the second phase space coordinates are equal to 0. Okay. So, if at some points, at one or more points in the phase space, these both become 0 at the same time, okay, then we can say that these points will be the fixed point for that system. And for our specific case, okay, the fixed points were given by v is equal to 0 and x dot is equal to v equal to 0 and v dot equal to x minus x cube is equal to 0, from where we can calculate the fixed points to be 0 and plus minus 1. Okay. Then we tried to find the trajectories of in the phase space of the evolution for the evolution of that system in the neighborhood of these three fixed points. Okay. So, the basic objective was that the fixed point is such a point if you prepare your system at a fixed point and you leave it to evolve, okay, and then it will not evolve any further, it will be in its initial state. Okay. So, it is fixed at its state. Okay. But if we prepare the system initially instead of the fixed point, okay, at a point which is a little bit shifted from the fixed point for both the phase space coordinates for this case, okay, then what will happen? Then of course, there will be some evolution, okay, the system will evolve, okay, the particle motion will evolve, the states of motion will evolve, but will there be a very interesting law, or can we even trace out some trajectory in the phase space for such type of evolution? The answer is yes, and that is exactly what we did in the last lecture. So, you remember that if you now do a very small perturbation with respect to the fixed point 0 0, okay, basically we linearize the system and we said that the perturbation is very small. So, x dot is equal to v. So, v dot is actually approximately equal to x, because x cube is now negligible with respect to x, okay, as x is a very small quantity. And then we found that the phase space trajectory of v and x, okay, actually phase space trajectory for the motion of the particle, okay, is given by a class of hyperbolae. Okay. Now, in the neighborhood of 1 0, when we did such small perturbations, okay, x prime, then we have shown also that we find the equation of an ellipse. Okay. So, if I now draw the phase space diagram, okay, for the motion of this particle, that is x and that is v. Okay. So, then what will happen, that 3 fixed points I denote by the red color here 0 0, okay, plus 1 0, let us say this is the plus 1 point for x, okay, and minus 1 0, which are symmetrically placed with respect to the origin. Okay. So, now we have just seen that in the neighborhood of 0 0, it is a hyperbola. So, let us say it has, so very close to this, maybe look like this. Okay. Okay. And now, the point is that if you just consider the phase space trajectory in the vicinity of this fixed point, which I now denote with a changed color green, then you will see actually there will be some ellipse. Okay. Remember, these pictures are very exaggerated, okay, these two pictures, because the hyperbolic trajectories should be applicable only very close to the 0 0 point, okay, like this, okay, where the displacement with respect to the fixed point 0 0 is very small, or the perturbation with respect to 0 0 is very small. Same thing here, but just for the sake of visualization we have drawn this. Okay. Now, I said you to do the same type of analysis for the fixed point minus 1 0, and if you also do that, you will see that it will actually behave like this fixed point, and you will also have elegant ellipses like this, okay, here. Although it should be, the ellipses should be very close to this fixed point. Now, if I even draw like this, this is not actually very false, because in a phase space trajectory always the continuity is a matter. So, the nature of the trajectories cannot abruptly change, and that is why even if you draw bigger hyperbolae like this and bigger ellipses like this, actually it is not a bad deal, because by the method of continuity actually the whole phase space can be thought to be ellipses very close to this fixed point, then there is a transition phase from ellipses to the hyperbola, okay, and finally it becomes hyperbola, and again when it goes to this fixed point, again it transforms to ellipse. Okay. There can be several, there can be some points where you can see that actually there is a very prominent phase of transition from ellipse to hyperbola or hyperbola to ellipse. Okay. Those points are a little bit subtle, and I will not go into very details on those topics. If you are interested, you can go through the very classical book, okay, by Strogatz, okay, on this subject. So, I am going to treat another problem, okay, and that is the problem of stability. How can we relate the concept of stability with that of the fixed point? So, for that what I will do, because I again said that this type of dynamical systems, the evolution of such systems, the determination of fixed points, and also finally the determination of the phase space trajectory and the stability, they are not only the exclusive property of classical mechanics. They are used in a very broad sense, okay, and they are also used in a very broad range of scientific domains, okay. And for that, what I will do, I will try to present a general picture of the concept of stability, which we can relate or connect to this phase space trajectories and also these equations of dynamics, okay. So, if we remember that, let us say we start with a very simplistic problem, that is, I have a 1D flow. So, you see, of course, the point is that no correspondence with classical mechanics, because in classical mechanics, whenever you have one phase space coordinate which is the position coordinate, you will also have an associated velocity, okay. Otherwise, the mechanics, okay, as a dynamical theory would not bear any meaning. But here I am simply thinking of any other arbitrary system for which the phase space itself is constituted of just one phase space coordinate, let us say that is equal to x, okay, and I have only one evolution equation x dot, which is a function of x, okay. In such case, now let us try to understand how to find the stability, okay. So, once again, what is the meaning of stability? So, the very general concept of stability or instability comes from the concept of whether any small perturbation given to the system, okay, imparted to the system, is actually getting increased or getting aggravated in course of time or not. If it is getting aggravated, then it is not stable. If it tries to continue to its original state more or less, or it wants to kill the perturbation, okay, then we are okay, we can say this is a stable system, okay. Now, if this is the case, then we, with that concept, we start by, we start to analyze this system. So, x dot equal to f of x, f is a function of x actually. So, this is the only single law of dynamics for this system, which is not necessarily a classical mechanical system, okay. And I am now saying that, okay, if this is true, then I also know that with a fixed point x is equal to x star. So, that means that at x is equal to x star, x dot is equal to 0, okay. So, and that is exactly is equivalent to say that, okay, it can actually have more than one roots, that depends on the whether this is linear or non-linear. Let us say it is a linear function, okay, then it will have just only one root. I am not constraining this to be a linear function, I am simply saying this is f x. Now, at some x star, okay, it has a fixed point, okay, that x star can have more than one values, okay. Now, if it is like that, then I can now be interested to check the stability with respect to that fixed point always, okay, because we know that fixed point is a point of eternal rest in phase space. If you somehow place the fixed point, at that point it will not move any longer, okay, nothing will evolve, okay. So, if I now disturb the phase space coordinates by a little bit with respect to the fixed points, then what will happen? So, I will now make x to be x star plus epsilon, where epsilon is very small with respect to x star in magnitude, okay. If I have this and x star is a constant value, so we also know that x dot will actually be practically equal to epsilon dot, okay, because this is constant. if I have this, and also I know that f x will then be f x star plus epsilon, and which is nothing but f x star plus df dx evaluated at x is equal to x star times epsilon plus half d2f dx2 x is equal to x star epsilon square and so on. Okay. Now, this one I know that is equal to 0 due to the property of fixed point, is equal to 0 by definition of fixed point. Okay. Then I have this thing and I have this thing. Okay. And now what I will say that this epsilon is so small that I can even neglect this part, this epsilon square part. So what can I do with this thing? I can simply say, okay, I can actually remember that x dot, which is now epsilon dot. So now I should not use implier sign here. Yeah. Now epsilon dot, which is equal to x dot, is actually equal to now f x star plus epsilon. Okay. And that is equal to df dx, okay, x is equal to x star times epsilon. So, you have actually d epsilon dt is equal to, I can call this thing as a constant beta is equal to beta, because this is df dx evaluated at a point x is equal to x star, which is the fixed point, times epsilon. So, I can simply say, okay, epsilon will actually be equal to a law which is epsilon 0 e to the beta t. Okay. So, you can simply see that this leads to a condition where the perturbation epsilon is growing with time is given by beta is greater than 0. Okay. So, that is the condition for unstable fixed point. Okay. So, if I have x dot is equal to f x in 1D phase space, okay, then I will just do the first order differentiation of that function with respect to x, okay, and I evaluate that at the fixed point. If this is positive, I have an unstable fixed point. If this is negative, I have a stable fixed point. Okay. So, I am just now going to do that if this is negative. Okay. So, if it is negative, then I have actually a stable fixed point. This one. Okay. Now, you can actually see that I can do this thing in a very small exercise. Let us say example, I have a phase space variable x dot for which the f x is given by x minus x square. Okay. So, I know that x dot is equal to 0 will give me x is equal to 0 and 1. Okay. So, because at x is equal to 0 and 1, x dot will be vanishing. Okay. And if they are vanishing, then these are the fixed point of the system, fixed point. Now, which one is stable, which one is unstable, or both are stable and unstable, like that? Okay. How can you say? So, the easiest way to check is you just take d. So, I can call this as f of x df dx, which is equal to actually 1 minus 2x, and this is now is equal to 1, that is greater than 0, okay, for x is equal to 0, and this is equal to minus 1, that is less than 0 for x is equal to 1. Okay. So, this thing actually said that for this case you will have an unstable fixed point and for this case you have a stable fixed point. Okay. Now, can we also do this for a system with more than one dimension, and that will be very much interesting for us because our classical mechanics will actually be one of the special cases of that system. Okay. So, we can also do that. What happens for a 2D phase space or flow, where the equations of dynamics are given by x dot equal to some f of x comma y and y dot is given as some g of x comma y. Okay. Now, this f and g, they are not necessarily linear functions. They need not be linear combinations of x and y, okay, and also they need not be linear functions of x and y. They can be, for example, x square minus x, okay. They can be x square plus y square minus xy, for example, this type of thing. They even need not be homogeneous, whatever. But whenever you put a very small perturbation with respect to the fixed point, then the resulting equations, okay, are expected to be linear, okay, because you then by hand will get rid of all the nonlinear terms for the perturbations. Okay. So, I am doing that. So, the same thing, let us say I have this system and I know that for that system x star y star, okay, let be the fixed point. Of the system. Okay. Then what I will do, I give a perturbation, give a small perturbation to both x and y as x is equal to x plus epsilon and y is equal to x star plus epsilon and y is equal to y star plus delta. You see, the small perturbations are always with respect to the fixed point values. Okay. If I do that, what will happen? So, of course, for f x y, you will actually find that you will have equations like, so first of all you will have, so f of x star plus epsilon y star plus delta, okay, and this expression will be then equal to f of x star y star plus epsilon times del f del x, okay, once again evaluated at x star y star, okay, plus delta del f del y plus other second order terms which we can neglect for very small epsilon and delta. Okay. I can do the same treatment also here for g, and so for g that will be g of x star plus epsilon y star plus delta will be equal to g of x star y star plus epsilon del g del x x star y star plus delta del G del Y. I forgot to write, that should also be evaluated at x star y star, that is evaluated at x star y star, and I neglect for the time being all the higher order terms. Okay. So, I cut the system here. So, I simply say that my expressions are given like this. Okay. If I do this, then I can write one thing that, so finally the set of the evolution equation of the state variables equations are given by x dot y dot, and x dot, which is f of x and y, is now be equal to f of this is 0, because that is the definition of fixed point, and this is also 0 also by the definition of fixed point. So, it will simply be equal to epsilon del f del x evaluated at x star y star plus delta del f del y evaluated at x star y star, and here the same thing for y. So, you have epsilon del g del x star y star plus delta del g del y x star y star. Now, you see, at this point I can write the whole thing in a matrix form, and I can say that I can write this x dot y dot, and I call that a vector of phase space velocity. So, if the phase space coordinates are x and y, then the phase space velocities will be x dot and y dot. So, this is the vector of velocity x dot and y dot, this column matrix, and that will be exactly equal to del f del x del f del y del g del x del g del y, all are evaluated at x star y star times epsilon and delta. So, you can see now there is a small observation by which you can easily find a very useful thing, that is x and y. So, x is x star plus epsilon and y is y star plus delta. So, x dot is nothing but epsilon dot and y dot is nothing but delta dot, because x star and y star, they are simply the constant values. And finally, therefore, we have epsilon dot delta dot is equal to del f del x del f del y del g del x del g del y evaluated at x star y star epsilon and delta. I have a matrix form for the linearized form of the equations of dynamics. If this is now a 2 cross 2 matrix, now it will also have 2 eigenvalues lambda 1 and lambda 2. Now, depending on the nature of the lambda 1 and lambda 2, actually we can think of the stability or the non-stability or instability of the fixed point. So, the rule is, it is somehow very close to what I did, where while talking about the stability or the equilibrium with respect to the potential energy of a particle in classical mechanics. This is something very analogous, okay. But here we are talking in terms of a matrix or the eigenvalues of a matrix which is consisting of the first order derivatives, partial derivatives, and this is called a Jacobian matrix. Jacobian matrix, okay. Whereas there we talked about the eigenvalues of a matrix consisting of the second order partial derivatives, okay, and we call that a Hessian, okay. But somehow both things are actually equivalent, you will also understand with time, okay. So the point is, so Jacobian matrix has two eigenvalues lambda 1 and lambda 2. If lambda 1 and lambda 2 they are real and positive, okay, and they are real and negative, okay, and there also can be two cases, distinct or degenerate. That means the same eigenvalues are not, okay, or repeating, okay. Another is complex, another is purely imaginary. Now for all usual dynamical systems, this Jacobian matrix actually they are consisting of real entries, okay. So that is why even if we have complex eigenvalues or purely imaginary eigenvalues, they should be always conjugate, okay, and conjugate, okay. These are the all possible cases, okay. Whether the eigenvalues are real or complex, if it has one part which is real and if its real part is positive for any of the eigenvalues, it will destroy the stability of the fixed point. So the fixed point will be unstable. I repeat, if whatever be the nature of the eigenvalues, if the eigenvalues are real, purely real or complex, but always having a real part, and if for one of the eigenvalues at least, if both of the eigenvalues have that, then I mean we do not think, again there is no doubt, but if at least one of the eigenvalue has a real part which is positive, okay, then this fixed point is not stable, okay, or an unstable fixed point. If the fixed point has two roots which are real and negative, this one, okay, so this is the case where we will find stable fixed points. Another case comes when you have purely imaginary case, and that is also a case where you can have actually oscillatory type of solutions, and you can have an orbit which is also in most of the cases a stable fixed point in most of the cases. Okay. Yeah. So in the next lecture I will give you some examples to discuss the stability of the fixed points in a 2D phase space flow. Okay. Thank you very much.